Hi guys, this lesson is for section 13.2. We are going to look at the remainder theorem and factor theorem when we are dividing polynomials. Our objectives for today are to check whether or not you have a zero or a root by using the definition of a root. So that's what I'm going to do first, is define a root. And then we're going to use remainder theorem to check for factors, as well as using the factor theorem to solve polynomial equations. So it becomes very useful to know the factor theorem to solve higher degree polynomial equations. Alright, so the definition of a root is given here. When you have a polynomial p of x, a number k is a zero if and only if p of k is equal to 0. Alright, this seems pretty, I think, intuitive, but here I have a picture. K is a zero of the function only if in the function p of x, in other words p of k, is equal to 0. So it crosses, graphically, you would see that it crosses the x-axis at that value. So, we're familiar with this term, but I do want to define it because we're going to use this concept to answer questions like question 1, where it says, is the square root of 3 a root of this polynomial here? Now, all you need to check, in order for it to be a root, you want to check, is f of root 3 equal to 0? Okay, so we're going to plug in f of square root 3, and we're going to evaluate this function at root 3 by just substituting in those values. And make sure you rewrite this, because you would not be using a calculator for something like this. And you can write that as 3 to the 1/2 to the 4th power, so this is simply 3 squared plus 3, just 3, square root of 3 squared is just 3, minus 21, and we end up with 18 plus 3 minus 21, which is 0. In other words, the square root of 3 is a root of f of x. Alright, so that's the definition of a root. It only works if and only if p of k is equal to 0, then you can assume that k is a root. Alright, let's discuss multiplicity of roots. This is something that we've seen already, because we've been graphing polynomial equations, polynomial functions, and we talked a lot about multiplicity before. So I just want to reiterate those concepts here with you now. But let's say we have this polynomial, it's already in factored form, and I see that x minus root 2 is to the degree of 1. So this has a multiplicity of 1. So this is a root of multiplicity 1. That's actually how you would say it, which is kind of weird. In other words, you can use the same phrase, root of multiplicity k or n or whatever, just to, where n just signifies the number or the degree of the linear term. Okay, so we would say that this is a root of multiplicity 2, and I like to just say things like the square root of 2 is a single root. That's the same kind of terminology you might hear. Negative 3/5 is a double root. And for this one, instead of saying triple root, sometimes you'll just see multiplicity of 3. So negative 4 is a root of multiplicity 3. Now, graphically, just to tie in some stuff that we've done before, I'm going to try to fit both of these things here on the page. Okay, so taking a look at our first factor, x minus root 2, the square root of 2 then is the root, right? And if we look at the square root of 2, which is this intersection here, where it crosses that x-axis, you're going to see that it looks like a linear function here. It looks like a line because this is to the first degree, right? It's to the first power. At the root negative 3/5, where we have a double root, we see it bouncing down. Okay, it comes up, it touches the x-axis, and it bounces down. When you have the odd degree here, this looks like a cubic function now. Alright, and basically just reiterating some concepts that we've already talked about. Okay, next up is the factor theorem. This is a really important concept for the rest of this lesson. But essentially, if you have a factor, so x minus b is a factor of a polynomial f of x if and only if f of b equals 0. So it's kind of reiterating what we talked about with the definition of a root, but now we're talking about factors. So x minus b is a factor of f of x if and only if f of b is equal to 0. In other words, if x minus r is a factor of f of x, then you can assume that f of r has to equal 0. And likewise, let's say you already know that f of r equals 0. That way, then you can assume that x minus r has to be a factor of f of x. All right, now you'll see that in in synthetic division. This would indicate that we're dividing a polynomial by x minus r, and we're checking to see if this is a factor. When you use synthetic division in whatever your polynomial is, if it's a factor, if x minus r is a factor, then you would have a remainder here of 0. So because we have a remainder of 0, then this is a factor of whatever the original polynomial was here. Okay, next, the remainder theorem, which is very closely related, just says that when you take a polynomial and you divide it by some linear term, x minus r, the remainder is always f of r. So in this case, if you were to use synthetic division, and you're dividing your polynomial here by x minus r, this value here, this remainder, is actually the same, it's equivalent to f of r. Okay, the remainder theorem just states that that's what the polynomial's function is equal to at f of r. If you evaluate f of r, you end up with your remainder from the same division of that linear term. So there are actually two ways to answer this question, number 2. I can just simply say, okay, if they're asking is 2 a root of this polynomial, which is very similar to the first question that we worked on. So we can check, f of 2, just like normal. We want to test to see, does this equal 0? If it does, then it's a root. Or we can use synthetic division. I think some teachers call this synthetic substitution when you do it this way. And I don't really care what you call it, but we're going to set it up both ways. And I want you to decide which one you like better. So if I check f of 2, I'd have 2 cubed minus 4 times 2 squared plus 3 times 2 plus 7. So I end up with 8 minus 16 plus 8 plus 7. So what does this give me? This is negative 8. Oh, sorry, that's a 6. Negative 8 plus 6 plus 7 gives me 5. Okay, so a little bit of evaluating there. I have to make sure I have all the order of operations correct. Now over here, since you're probably very proficient now with synthetic substitution, when you carry that down, multiply here, add these, multiply again, you get negative 4, add, and then multiply one more time, you see that you have a remainder of 5. I think I went through that a lot quicker, and I also was talking, out loud, so you guys would probably do that in like 2 or 3 seconds, tops. So you're seeing the remainder theorem at work. Basically, when you divide that polynomial by whatever that linear term is, so x minus r, in this case it was x minus 2, we're dividing this polynomial by x minus 2, the remainder, 5, is the same as if you were to evaluate that function at this specific value. Okay, so f of 2 is equal to 5, and you're seeing that same value in your remainder for your function. All right, now this next question here, it says find f of negative 3 to determine whether x plus 3 is a factor of this polynomial. Because we know that if f of negative 3 equals 0, then we have x plus 3 as a factor. Okay. Now again, you can use synthetic substitution. I think that's just faster. In this case, let's say I tried to do f of negative 3. I have 2 times negative 3 to the 4th power plus 5 times negative 3 cubed minus 2 times negative 3 minus 8. Now without a calculator, it's not impossible. This is a positive 81 times 2, so positive 162. Negative 3 times 3, negative 3 cubed is negative 27, times 5 is negative 135. Yeah. And then plus 6 minus 8. So it's not like this is impossible. I think it's tougher, but it's not impossible. We should end up with, let's see, what is this? 17 plus 6, 23 minus 8. Wait. Oh, sorry, 27 plus 6 minus 8. So 25. Okay, so we end up with f of negative 3 equaling 25. Now, if I had done that same problem here, just using synthetic substitution, I would end up with a remainder. I should end up with a remainder of 25 here as well. So I'm going to stick that negative 3 on the outside. 2, 5, negative 2. And then be really careful, oops, not here, be really careful between here. You should have a 0, a placeholder between that, and if you don't, you're going to get the wrong remainder, so make sure you always have a placeholder there. And then I can go through this a lot quicker, even though I'm talking out loud and I'm not really paying attention to what I'm writing. It's still faster for me to do it this way than it was for me to evaluate over here. Okay, so I don't know, it's up to you, but I would definitely recommend using synthetic substitution. Alright, so what we're seeing here is that f of negative 3 equals 25, which means that x plus 3 is not a factor of f of x, because we're not seeing a remainder of 0. Alright, the next type of question that you might see is something like question 4. Using the factor theorem or the remainder theorem is very helpful when you're solving polynomial equations. So when we look at this, we know that in the question here it says, knowing that negative 2 and root 2 are roots, we are going to solve this 4th degree polynomial. Okay, so let's start with the fact that if negative 2 is a root, that means x plus 2 is a factor. Then if x plus 2 is a factor, we should, when we stick this into our synthetic division here, we're going to put a negative 2 on the outside. We have 1, negative 2, negative 10, 4, and 16. Okay, and if I use synthetic substitution here, I should end up with a 0. So I'm going to predict that I get a 0 here because it's telling me that x plus 2 is a factor. In other words, negative 2 is a root. Okay, so we'll check here. And when I multiply here, I get negative 2. So negative 2 times negative 2 is 4, 8. 8 times negative 2 is 16, and when I add these, I do get, in fact, a 0. Okay, so what this is saying now is that after I divide my polynomial by x plus 2, okay, after I divide my polynomial by x plus 2, I am left with a new polynomial. Okay, so f of x now can be factored into x plus 2 times, remember this has a degree 1 less, so x cubed minus 4x squared minus 2x plus 8. So f of x, this original polynomial here, can be rewritten as the factor of these two polynomials. Okay. Now, I'm going to do the same thing, knowing that the square root of 2 is another root of f of x. Now, obviously, it can't be a root of this polynomial, so it's got to be a root of this remaining polynomial. So now I do the same process. So what this is saying now is that I should be able to split this up into x minus root 2 multiplied by some other polynomial here as well. So we're going to use synthetic substitution, or I'm sorry, synthetic division here. We have negative root 2 on the outside. Whoops, I'm sorry, it's actually just a positive root 2 because I read it wrong. It's the square root of 2 is a root, right? Which means that the linear factor would be x minus root 2. So anyhow, we'll put root 2 on the outside of this synthetic division. Now, again, you're going to now divide this polynomial by square root 2. So we have 1, negative 4, negative 2, and 8. And I want to space this out a little bit. And don't be worried just because you have, an irrational number on the outside doesn't mean that it changes the way that you solve using synthetic division here. We're going to still carry down that 1, and we're going to multiply 1 times root 2, and we end up with root 2. Now when I add negative 4 plus root 2, I simply write it like this. Now when I multiply negative 4 plus root 2 times this times this root 2 on the outside here, I end up with negative 4 root 2 plus 2, okay, because I'm just distributing the square root of 2 here, so that's going to be negative 4 root 2. Root 2 times root 2 is a 2. So that's where this is coming from. And now when I add these two together, these 2's are going to cancel out, and I'm left with just negative 4 root 2. Now when I distribute here negative 4 root 2 times root 2, I end up with negative 8. when I add 8 and negative 8 together, I get a 0, which is what I want, right? I know that this is supposed to be, x minus root 2 is supposed to be a factor, which means my remainder should be 0, all right? So now I'm left with, let me erase all this, I am left with a quadratic here. So let's rewrite this quadratic that's left over, and remember it's a quadratic left over because we're taking this polynomial, which started with an x cubed, so this degree here is 1 less, so that's x squared. And then plus a negative 4 plus root 2 times x, and then minus 4 root 2. This is just a constant. This last number here is just a constant. So this is what our original f of x is going to factor into now. Okay, here are all the factors of f of x. Now, what I have left to do is solve this equation, right? I'm supposed to solve here when f of x is equal to 0. So we have already two roots, one at negative 2, one at the square root of 2. And now inside here, I would work to find additional factors. Now, in this case, it's not really quick to try factor theorem again, because you can simply factor a quadratic or use quadratic formula. So basically what you want to do, and I'm not finished yet with this problem, but I want to recap what we're doing here. What you want to do when you have a high degree polynomial like this, x to the 4th power, you are going to use your factor theorem to try to reduce this into a quadratic. Okay, so let's say it started as x to the 5th. Well, we would need to have at least 4 factors to get it down to something that's reducible, a quadratic term that I can either solve using quadratic formula or factor, all right? That's the goal. So here we started with x to the 4th. We took one of our factors, we divided that out, we resulted in this polynomial here, and then we took that polynomial, we factored it again using the root 2 here, or x minus root 2 is the factor. And we're left now with this quadratic. So all we have left to do with this particular quadratic is to try to factor it. Okay, so when you're looking at this, I know it looks really tough, but the fact that this linear term here can be rewritten as x squared minus 4x plus root 2x minus 4 root 2 means that obviously x times negative 4 and x times root 2 have to be your original terms. So this is going to be x minus 4 and x plus root 2. Okay, this is how we get negative 4x and a positive root 2x here. And then if I multiply the two constants, I get negative 4 root 2. So this would be the factored expression for this quadratic here. And now I have that original x plus 2, x minus root 2. And I'm going to set that equal to 0. So I have now solutions. X equals 4, x equals negative root 2, x equals negative 2, and x equaling positive root 2. These are all the solutions to that equation. All right, so I know that seemed like a long one. Eventually you're going to get so efficient at this that'll be very quick for you to be able to do. But make sure you understand the process, otherwise you'll be very confused. All right, problem 5 is a short one, so we're ending on a very quick problem here. It says to find a polynomial with degree of 3 and a root of 1 with multiplicity 2 and a root of negative 2. So I'm finding a polynomial, not just the polynomial. There's many polynomials that would fit this, these, I guess, call them constraints, but these conditions, it's a better word for it. So we have to have a polynomial with an overall degree of 3. That's important here. We have a root at 1, which means that a factor for this polynomial would have been x minus 1. This root is supposed to have a multiplicity of 2, so we're going to put that as an x minus 1 squared term. And we also have a root at negative 2, which means that x plus 2 is another factor of this polynomial. So far I have x minus 1 squared and x plus 2 as my function, some function, let's call it f of x. I don't care what you call it. Now, this overall has a degree of 3, so this already satisfies this original condition here. So we can't add any more terms here. The reason why I say find a polynomial is because I could stick, a negative on the outside of here. I could put, let's see, I could put negative 3 billion out here, whatever, and it still meets all of these conditions, that were given in the beginning. So That's why there's really an infinite number of polynomials that you could write that satisfy those conditions. But there's my answer. And that's the end of the lesson. I will see you in class tomorrow, and get ready to work.